So if we open this up, this is old. Some of these are old videos that I've done in other classes. So these are some video resources. So this is the roller coaster that we've seen. This is the Hewitt-Druitt circular motion, Hewitt-Druitt's centrifugal force. This is that bus on the banked curve. This talks about why highways or curves are banked. Looks at centripetal force and some solar system type stuff. So I've put all that there. Then I've run across a good set of videos, and I know it seems a little odd, but they're called Organic Tutor. And they've got one on torque, static equilibrium, they do the sine problem, they do the ladder problem, they look at moment of inertia and rotational motion. So I've given you guys links for those as well. So all of those are in there. And these two are older or previous classes where I've done rotational motion out of the other textbook. So these are in the other textbook and not our textbook that we're using. There's Wednesday's lecture, which we did the earth problem. It's there. And then over in WebAssign, I have input now. Everything that was in WebAssign is now in Blackboard, and so your grade has been updated, so you can look at where your grade stands. And you want to look at percent for grade. So that's in there. And then I have posted the rotational motion homework. So it's now in Blackboard. And I've got it due at 11 p.m. on Wednesday. So you should be able to start tackling it. And we'll get through starting of torque today and defining moment of inertia. But then on Monday, we'll start diving in moment of inertia and start moving on into the next chapter. So this rotational motion is just on the current chapter. So hopefully that gets us back, caught up to where we need to be, and gets us going from that perspective. All right, so we started the earth problem last Wednesday, because today is Friday. So we got the earth problem there. And I said I wasn't going to start the next topic until today, and that's what we're getting ready to do. So way back when we first started potential energy and work, I'm pretty sure I did the lever problem. So we got a lever, and I could put a big weight here. So we could put a feed sack at the bottom here. Let's just make it a feed sack. And a feed sack's going to have 80 pounds. This is a big feed sack. Some feed sacks are 40 pounds. Some feed sacks are bigger feed sack. And we're going to want to lift it up to a height H. And I'm going to apply a force on my lever to go to that height H. So when we looked at work, remember work was force dot product a distance, and the work that was done here was mgh, right? It's going to be that we had to move the force, and so if we're going h, but if I applied a force over here, and let's say that this was 2h, the force that I had to apply was going to be my force applied times the distance. So my mgh was going to be my force applied, which is our question force, but my distance was 2h. So the force applied is going to equal mgh divided by 2h, which just is going to be 1/2 the weight of my object that I was trying to lift. I only have to apply half that weight. So I only have to apply 40 pounds of force to lift an 80-pound object. So this was from an energy point of view. And one of the things that we looked at here was our dot product. And the dot product is a scalar. And that's a little bit different than what we're going to fixing to deal with. But one of the things that we didn't talk about when I brought up that lever is I actually get a rotation. I'm going to go a rotation around that pivot point. Okay, I get that rotation around the pivot point. And we talk about the right hand rule. I will, just a second. We get the right hand rule. And the right hand rule says that if I've got a rotation and I take my fingers and I rotate it around, in this case, the rotation is going to go into the paper and we're going to go around that way. If I did the rotation the other way, I'm going to come out of the paper and I'm going to go the other direction. And I think we've even talked about it, that if I go this direction around the circle, which is clockwise, we arbitrarily call that negative. And if I go around the circle the other way, counterclockwise, we call that positive. And that's getting back to this right-hand rule giving me good direction associated with it. So that's one of the reasons that we look at the right-hand rule. So we're dealing with that pivot point. Now, most of us have dealt with this at some point or fashion. I've got a teeter-totter, and I have a fulcrum, some sort of fulcrum, and I have a mass over here, and I've got a mass over here, and we know that if I move this mass along this direction, no matter where my fulcrum is, I can make this teeter-totter balance. I can keep that teeter-totter balance, because we've played that game. That's why the little kid can balance a bigger kid. That's why we've played that game numerous times. We also know that, and we've been talking about it, because we actually did one of the Wile E. Coyote things, and we actually talked about it. So if I've got a big, huge rock, irregular shaped rock, and I'm sitting on top of a tabletop or a cliff, as long as my center of mass is over this pivot point, my rock's going to balance. And so we've been talking about that center of mass, and that's one of the reasons why we deal with center of mass. I think I've even shown people that if I have a set of books, and we got our center of mass of this book, and then I put in another book, and as long as the center of mass of these combined books stays over my tabletop, I can actually develop a situation where I could have, here's my book, and then I do my book, and I do my another book, and then I ultimately get a book, and as long as I keep the center of mass of the system over the edge of the tabletop, this stuff won't fall over. It won't tip over, it won't fall over. So we can play with those center of masses, which is why the center of mass becomes a real important piece. But let's look at our situation. So we're going to define something called torque. Torque is a vector quantity. Something that we also look at torque, it's also referred to as a moment. Okay? We use this in engineering typically. In physics, we're going to use it as torque. And we've all played with torque, because if you've ever had a flat tire, you have one of two types of tire irons, right? You've got that type of tire iron, and you've got the type of tire iron that looks like this, the cross type of tire iron. You've got those two types of tire iron. And I will tell you that everybody has a preference for which tire iron they use. And I will tell you that most men like to use this one, and most women like to use that one. And it's related to how we're going to accomplish the torque. Because both of these are going to accomplish the torque the same way. Except for men, you typically, now my daughter's a little different. My daughter's also ambidextrous. My daughter will prefer this one, because in order to get this to turn, I can apply a force this way and I can pull up on a force. I'm going to end up getting the same torque at the end, but I'm balancing it out with both arms. This one, I'm going to put both arms on one end and I'm going to be able to move my tire iron that way, or more likely I'm going to jump on it instead in order to break that lug nut free. But the same thing is going to be dealing with, I'm applying a force at the end of this, and there is a lever arm associated with it. Over here, I'm applying two forces, but I still have the lever arms on either side. So the way I think of torque is a force acting through a distance rather than the force acting over a distance. So work, remember work was force dot distance. Torque is a little different. Torque is going to be a vector product, and we're going to look at that lever arm. This is our lever arm distance. And if I go back and I look at vector mathematics, okay, you've had this in college algebra somewhere, you might see it in trig, you might see it in calculus somewhere, but one of the things that we know about cross products is A cross B does not equal B cross A. That doesn't work. So A cross B does not equal B cross A. In fact, A cross B is going to equal negative B cross A. And that's where the right-hand rule comes into play. And the result of this is another vector. So we talk about this being the cross product or the vector product. So we get that as the cross product or the vector product. And if you remember along the way, somewhere along the way, when we dealt with vector products, if I have an I plus J plus K, and I did a vector product with another I plus J plus K, and we did that along the way, I get an I cross I, that equals 0, mathematically. And we'll actually draw the picture here in just a second. If I get a J cross J, that equals 0. And if I get a K cross K, that equals 0. But if I do an I cross J, I get K. If I do a J cross K, I get an I. And if I do a K cross I get a J. And this goes back to Cramer's rule. Because in Cramer's rule, remember, I could have a matrix and have an I, J, K, and I can have an A, B, C, and I can have a D, E, F, and I could end up with a vector product associated with it. So that's one of the things that we end up doing with torques or moments is we end up with that vector product. So I get that vector product. So torque, then, we're going to define torque a couple of different ways. So torque usually is a big tau with a vector product, and it's R cross F. And remember when I had work, which was F dot D, this was a Newton meter, and this became a joule. This, if we write the units in the right way, we get meters, newtons, but we typically, by convention, write it Newton meters, but these two things are not the same. Because one is a vector quantity, one is an energy, one is a scalar quantity, one has direction. So if I think of torque, the force acting at a distance, I've got to keep track of this. Now in the English common units, it's foot-pounds. We actually write it right in the English units. We don't write it right when we're dealing with metric units. So we end up with that. So let's look at what's happening. So if I have a vector R, and I'm going to apply a force, one of the things I can do with my force is I can move my forces along a line of action. So I can have that line of action here. And if I move this force along this line of action, this is going to be my force, and this is my R vector. This angle right there, I can look at the magnitude of the torque, is going to be RF sine of the angle. That's going to give me the magnitude of the force that's being applied. And one of the things that we know is if I look at it from that perspective, if I have R and I have my force applied here, this is R and this is F, sine of the angle is 0, or sine of the angle is 0 is going to equal 0. This becomes my I cross I. So if these are in the same direction, that's going to be 0. But we know from experience, and we've done it before, that if my force is applied here, perpendicular, that's the sine of 90 degrees, and that equals 1. So my maximum force is going to, my maximum torque is going to come when the force is being applied perpendicular. Okay, my force is going to be applied perpendicular. And we've played with this over time, and we've had that, and we've have experience doing that. So one of the things that you can look at, so if I have my R vector, and I've got my force vector, this is going to be my angle, but then I can look at it as this, and this is going to be R perpendicular, and this becomes what we do as the moment or lever arm. And this perpendicular part, when we get to statics, becomes really, really important. Because I can simplify a lot of problems if I deal with my moment or lever arm versus doing the traditional torque calculations. So from an engineering point of view, this becomes really, really important. So you can look at these lines of actions, because I can move my forces along those different lines of actions, and I can get those pieces back and forth. Some other things from a vector product point of view. So we've already done I cross I, which is equal to J cross J, which is equal to K cross K. Those are 0. And I get I cross J is equal to K. Now if I get J cross I, that equals minus K. And we can get that right-hand rule. Okay, that right-hand rule, if I'm moving my hands around that right-hand rule. I can do A cross, vector A cross C plus B. That's going to be A cross C plus A cross B. And then if I take a scalar M and I do A cross B, that's going to equal MA cross B, or it can equal A cross MB. Just some of the mathematics that might help you out along the way. So let's go back to look at a couple of things here. So let's take the teeter-totter. And I'm going to have a mass on this end. going to say that that mass is 20 kilograms. And I can put a mass on this end. And we're going to say that that mass is 40 kilograms. I know that this mass is placed 1 meter away from the fulcrum. I don't know this one in order to get the teeter-totter to balance. Couple of things. We talked early on about the summation of forces equaling 0, which meant mass times acceleration equaled 0. And we said that that was a special case. And the problems that we worked with on that was I had a weight or a sign or something hanging from, so this was a weight and this was, let's say it had a 20 pounds. We could find tension in the rope because we knew we had to have forces equal but opposite, so we knew that the tension in the rope was 20 pounds if this thing wasn't moving. And that was what we referred to as our first condition of equilibrium. Now the fun part is we can do the same thing here. We could actually say, if we know that that's 40 kilograms, we know that's 20 kilograms, we could actually ask the question, what's the force being applied at the pivot point? Well, that's easy, because we can do the summation of forces in the y direction. So we know that we have to have 20 kilograms times gravity, 9.8, and that's going in the negative direction. We've got the force at the fulcrum minus 40 kilograms times 9.8, and that's meters per second squared. Okay, so now I get the force at the fulcrum is going to equal, it's going to be 60 kilograms times 9.8. If I plug that into the calculator, I get 588 newtons. But one of the things that we don't know is, if I just put this box anywhere on this other board, a couple things will happen. If I don't put this box such that I end up with the center of mass right above the fulcrum, if I put this box too close, it'll rotate that way. If I put this box over here too far, it'll rotate that way, and I won't be in equilibrium. I'm not going to be in equilibrium. So I get my second condition of equilibrium. And my second condition of equilibrium is that the sum of the torques, or actually we refer to it as the sum of the moments, on the static side, has got to equal 0. And if we look at what happens here, so if we look at Newton's second law that way, we get F is equal to ma. But my torque can also be related back to an angular acceleration. So I can get, and this is still a vector quantity, this is still a vector quantity. These are still going to be proportional, so I have parallelism. I get parallelism, and what we actually refer to this is I, which is what we call a moment of inertia. In the next chapter, we're actually going to calculate those. Okay, we're actually going to calculate those, but you guys have dealt with moments of inertia before. So think for a second. If I've ever held the bicycle wheel between my hands and have it start spinning, trying to keep it straight, if I turn it, it wants to come right back, right? It wants to come right back to where I'm at. If I'm riding a bicycle, My front wheel does the same thing. If I turn, my bicycle wheel wants me to come back upright. That rotational motion of my bicycle wheel has a moment of inertia. If you do an experiment, we'll come back to this. And this is something you guys can do and have some fun with, right? If I take a ramp and I take a can of cream of mushroom, tomato soup, something along those lines, and I put a can right next to it, so if I've got a can right here, and then I put a can of, say, vegetable soup, and I roll them down the hill, you find that they won't roll at the same rate. They aren't going to roll at the same rate. I can also do a hoop, and the hoop's not going to roll at the same rate. And we're talking about how it's going to roll, and it's going to be related to the actual configuration of what's happening. So in my can of condensed soup, it's more solid, right? It's more solid. It's pretty solid. Things aren't going to move around a whole lot. But if I have a can of chicken noodle soup or I have a can of vegetable soup, I got particles that are free to move, and they're going to go into a different location. So how this is going to roll down the hill is going to be very dependent on its moment of inertia. The other thing is if you've ever spun, okay, if I have a baton and I spin it this way, it has a different moment of inertia than if I spin it this way. Or if I'm spinning it around this end, going around, it's going to have a different moment of inertia than if I'm in the middle. And we're actually going to do some calculations to show those differences. The other thing is that when I'm rolling, we know we have conservation of momentum, right? The energy for this thing is going to be different as I'm going down this hill. It's going to be different. The energy is going to be the same. But if this can is just sliding down the hill versus rolling down the hill, something's going to happen a little differently. In fact, the rolling can will get down there faster than the sliding can. And so we'll have some differences associated with how that moment of inertia occurs. So my torque has a very similar thing to what's going on. And so I've got an inertia and I've got an angular acceleration. And this is going to be related to mass, but it's how that mass is configured and where that mass actually physically is. And we will actually play with that a little bit. So coming back to this problem, and most of us have done this problem in algebra, right? This is an algebra type problem. I know where this one is, and I know where this one needs to be in order to balance it out. So let's balance it out. Let's go ahead and do it. So what we've got is, in order to have my condition of equilibrium, I have to have the sum of the torques have to equal 0. So the torque on the left has to, or minus the torque on the right, has to equal 0. And we said torque, okay, we said torque, magnitude of the torque is going to be R times the force, sine of the angle. But if I'm dealing with my teeter-totter problem, sine of the angle is going to be the sine of 90 degrees, is going to equal 1. So the magnitude of the torque is going to be the lever arm times the force. So the torque on the left is going to equal mg, the distance away. The torque on the right is going to be mg, the distance we don't know. So I'm going to have mg distance is going to equal mgx. What's good news is g's cancel, so I don't necessarily have to plug in those and figure those out. And I've got 20 kilograms over here times 1 meter is going to equal 40 kilograms times the distance I don't know. And my 20 kilograms divided by my 40 kilograms times my 1 meter is going to equal 0.5 meters is equal to X. Which we kind of knew already. Right? We kind of knew that already because we've done that intuitively over and over and over again. That we play with those pieces that we have to watch out what's happening. So we can do a tire iron problem just for grins and giggles. Okay? So here's tire iron, right? And we're looking from above here, and I'm going to apply a force. And I'm going to apply a force of 200 pounds at the end. And my typical tire iron is what? If I've got a tire iron, if I got a short one, it's about 1.5 feet. If I got a good one, it's about 2 feet, right? So we'll do it as a 2-footer. At 2 feet. And one of the things is if I'm going this way, if I'm putting my force down and I'm rotating here, this is going to cause a rotation in that direction. I'm going to get my lefty-loosey because that's what I want. And that's going to have my nut rotate around this way and it's going to loosen up. And so the torque that is applied, because this is perpendicular, right? This is perpendicular. The torque that's applied is going to be 2 feet times my 200 pounds. And that's going to give me a 400 foot-pound of torque. Which is exactly what I want in order to get my tire lug nut loose. We do the same thing. Okay, so this is a funny story. So, anybody ever look at a ball hitch? So I got my ball hitch. Okay. We are traveling in the panhandle of Oklahoma with a 2-horse trailer behind us. And we discover that my ball hitch is loose. We discovered that my ball hitch is loose. Not a good thing when you have 2 horses in the back of the trailer. Bad plan. Alright? The other bad plan is I didn't happen to have a wrench that could go around my ball hitch. More bad plan, right? So, we each pull in, so I get it as tight as I can with my hand. We try to get it as tight as my hand, and we're going to stop and check it every now and then. And we're hoping that by the time we get to the next little town or the next convenience store, we find somebody who's coming in from the field that happens to have a wrench on their flatbed trailer or their flatbed pickup truck. So we did. We happened to find a young man who had a very nice wrench. And I'll tell you, this wrench was a good old crescent wrench that actually would fit. And I kid you not, this sucker had a 3-foot length. Okay? Guy was a big guy. Okay? Guy was a big guy. And he applied a heck of a lot of force on that end of the wrench. I'm guessing he applied more than 200 pounds worth of force. I'm guessing he applied more than 300 pounds of force on that lovely little wrench. And he gave it a nice little push. We got a tight nut. And he said, "Ma'am, I don't think I got it very tight. You may want to have that checked." I have yet to actually remove the nut, and it has hauled numerous things. I didn't worry about it too much. I'm just glad he didn't shear it off, because that's a strength of materials problem. Just glad he didn't, even I could have gotten it tight on a 3 foot. So I right now I'm doing demolition. I'm using a lot of torque. I have a cheater bar. My cheater bar is 4.5 feet. Guess what? I'm doing all right. Tools are great things. Tools are great things. So that gets us pretty much through this chapter. We will start looking at this rotational stuff and start looking at rotational motion on Wednesday or Monday. My other class is a Wednesday, Friday class. You guys are Monday, Wednesday, Friday class. I will start getting the homework out. You guys get to start probably look at a quiz on momentum here pretty shortly so that we got those kinds of things going. And that gets us pretty straight and gets us going for today. I don't want to start doing moments of inertia yet, because that's the fun part. So we'll see you all on Monday. Monday? Huh? Nah, Gooseneck still has the same problem. You still have loose bolts. Still have loose bolts, but that's always been my favoritist. The guy says, I don't think I got it very tight. I think you got it just fine.